We've looked at basic probability. We've looked at A or B. Now we're going to look at something called conditional probability. So approximately 15% of adult men in the US are more than 6 feet tall. Therefore, if a man is selected at random, the probability that he is more than 6 feet tall is 0.15. Now, assume that you learned that the selected man is a professional basketball player. With this extra information, the probability that the man is more than 6 feet tall becomes much greater than that 0.15. So a probability that is computed with the knowledge of additional information is called conditional probability. The conditional probability of an event B given event A is denoted as such. That means the probability of B given that A has occurred. Now, the way we compute it is actually fairly easy. So the official formula would be we'd find the probability of A and B, so the probability somebody's over 6 feet tall and a basketball player, divided by the probability that they're a basketball player. In layman's terms, what we're going to do is we're going to take the outcome, number of outcomes for A and B, for that overlap, divided by the number of outcomes for A. So what it's doing is it's kind of reducing our sample space. Consider the following table, which presents the number of US men and women 25 years old and older who have attained various levels of education. A person is selected at random. What is the probability that a person is a man? Well, the probability that they're a man, we need to take the total number of men. And by the way, this is in millions. So the probability that it's a man we need to get some totals here. So we need to add up how many men we have, and it'd probably be good to go ahead and add up how many women so we can get a total amount. So I'm going to go down and go 14 plus 29.6 plus 15.6 plus 7.2 plus 17.5 plus 10.1, and that's 94 million that way. The women, I get 101 million. So that means our total is 195. So the probability that we just randomly pick someone and that person is a man would be 94 out of 195. What is the probability that the person is a man with a bachelor's degree? So the probability that it's a man with a bachelor's degree that would be 17.5 out of 195. Let's look at these in decimals just real quick. That's 94 divided by 195. 0.482. And man with a bachelor's degree out of the whole population is 0.0897. Now, what is the probability that a person has a bachelor's degree given that he is a man? bachelors, given that it's a man. Bachelors, given that we have a man. So the number of people that are man with a bachelor's was 17.5, divided by the total number of men is 94. So if we know the person's a man, what is the probability that that man has a bachelor's? And I got 0.86. Notice it's higher because we've already reduced the sample size to only have men in it. Now, if you're looking at the formula and you're going, well, that formula isn't quite what we did here, it kind of is. If I use the formula, the probability that it's a man and he has a bachelor's divided by the probability that it's a man. Well, if I was doing it the formal way, I would be doing 17.5 divided by 195 over 94 divided by 195. And notice the 195s could cancel out. I'd have 17.5 over 94. So I like to think of it more in this way. The number of outcomes for both divided by the number of outcomes for what we were given. Now, the general method for computing conditional probabilities provides a way to compute probabilities for events of the form A and B. So let's see how that works. If we had, so we're talking about the probability of B given A was the probability of A and B divided by the probability of A. Well, if I multiply both sides by the probability of A, I get that the probability of A and B is going to be the probability of A times the probability of B given A. Among those who apply for a particular job, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. So find the probability that an applicant is offered a job. So the probability of being offered the job we start with the probability that they got an interview. Times the probability that they were offered a job. But notice that that's just if they've been interviewed. So the probability of offered given that they were interviewed. So the probability that they were interviewed was 0.1. Whoops, that's a 0. And the probability that if they're interviewed, they get offered the job is 0.25. So the probability that they were offered a job, we have to know that they were interviewed first. That's 0.1 times 0.25. The probability that they're going to be offered a job is 0.025 because they have to get interviewed first. Now, when we're talking about this conditional probability, we also need to think about an item called independence. Two events are independent if the occurrence of one does not affect the probability that the other event occurs. If the two events are not independent, we say that they are dependent. Determine whether the following events are independent or dependent. A college student is chosen at random. The events are being a freshman and being less than 20 years old. If the student is a freshman, the probability that the student is less than 20 years old is greater than for a student who's not a freshman. So these are not independent. They could affect each other. A college student is chosen at random. The events are born on a Sunday and taking a statistics class. Is being born on a Sunday going to have anything to do with whether you take a statistics class? No, these would be independent. Now, why does that come into play? Well, if they're independent, then they're not affected by each other. So if they are independent, the probability of them both happening, they're not depending on each other. It's just the probability of A times the probability of B. According to recent figures from the US Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, and 26% in LA. If one person is selected from each city, what is the probability that all of them are under 18? Well, does it matter if a person is from New York? Does that affect them being under 18 in Chicago? Or being under 18 in Chicago, does that affect the number of people who are under 18 in Los Angeles? No, these are independent. So the probability of someone being under 18, I'm going to abbreviate, from New York and from Chicago and the person from LA, we would take 0.235 times 0.258 times 0.260. So this is the probability that all three people are under the age of 18. I got 0.016 basically. Is this an unusual event? Well, yes, that's lower than 0.5. Yes, this would be unusual. Now, I do want to say one thing. Just be careful about mutually exclusive and independent. We don't want to confuse those two items. Okay. Now, when we sample two items from a population, we can proceed in either two ways. We can replace the first item drawn before sampling the second. This is known as sampling with replacement. The other option is to leave the first item out when sampling the second one. So think of a deck of cards. I can either look at the card and put it back in the deck, replacing it, or I can look at the card and put it to the side. So when we're sampling with replacement, the draws are independent. When I put that card back in the deck, I could draw it again, right? Okay. If I take that card and put it to the side, for one thing, it reduces my sample size, right? It's changing what's left. So they are dependent of each other. When sampling with replacement, each draw is made from the entire population. So the probability of drawing a particular item on the second draw does not depend on what we had on the first draw. When a sample is very small compared to the population, less than 5%, a rule of thumb is that the items may be treated as independent. So let's also look at least one type probabilities, because this one gets kind of tricky sometimes for people. Sometimes we need to find the probability that an event occurs at least once in several trials. Now, that can take some work sometimes, but the easiest way to calculate these probabilities is by finding the probability of the complement. Because remember that the complement of at least one event is that no events occur. So to compute the probability that an event occurs at least once, find the probability that no events occur. And then you'd have 1 minus the probability of no events. That would give you the probability that it occurs at least once. So items are expected for flaws by 3 inspectors. If a flaw is present, each inspector will detect it with a probability of 0.8. The inspectors work independently. If an item has a flaw, what is the probability that at least one inspector detects it? Okay, so I need to think about that. If at least one inspector detects it, the probability of at least one detects would be technically 1 minus the probability that none detect a flaw. So they fail to detect the flaw. So I'm going to think about it this way. That means it's the probability that the first fails times the probability that the second fails times the probability that the third fails. So 1 minus the probability that the first fails. So he's going to detect it at a rate of 0.8. So failing to detect would be 0.2. So for each of those inspectors, failing to detect would be a 0.2. So 1 minus 0.2 times 0.2 times 0.2, 1 minus 0.2 times 0.2 times 0.2 gives me 0.992. And that kind of makes sense. At least one defect is found. Yeah, it's going to be pretty high. All right. A fair coin is tossed 5 times. What is the probability that it comes up heads at least once? Well, the probability that we get heads at least once would be 1 minus the probability of no heads at all. That'd be the probability of tails all 5 times. So 1 minus, what's the probability of tossing a coin and getting heads? Well, it's 1 out of 2 times 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 1 out of 2. All 5 times they get tails. That'd be 1 over 32, actually. 1 minus 1, 1 out of 32 is 0.962. 6, basically 9.